Hi everyone, welcome to our first lesson going back on C5 since before Christmas. So I'm sure you're feeling a little rusty on this, I certainly am. So if you are coming to this video as your first task in your lesson, please can you go away, no offence, and go read back through your notes. So our topic started on the 26th of November in your books. And I'd like you to, before you watch this video, go and read through what you wrote before Christmas. Just remind yourself of it. If you've already done that and you're joining me in this video, fantastic. Hello, welcome. So today we're going to be looking at the effect of concentration on the rate of reaction. Sorry, that's my chair, it's very squeaky. So if you can please title and date. It is not the 23rd of September 2019 today. I'm not sure when you're seeing this, but just write whatever day it is then. And yes, so let's crack on. So, just a quick reminder, in fact, let's go through rate of reaction. Rate of reaction is how quickly you are either producing something in, do you know what? I'm going to write this down. Yes, I am. Let's have a blank slide. Oh, and I'm getting my Apple Pencil out. Oh, aren't you lucky you get to hear my train of thought? Hear all the rubbish that I think whilst I'm getting my Apple Pencil out. Okay, wonder if it has any charge. It has charge, look at that. Okay, right, let's write down basically what we know so far. So, rate of reaction. How quickly, effectively, you can either A, make a product, or B, use up a reactant. Now it's affected by lots of things, but the key things is that it is oh my god, I'm so rusty on this. I'm so sorry everyone. Let's get back on it. Right. A reaction is caused by collision theory. So reactions happen because of collision theory. Now, collision theory states that particles must collide with each other with the right amount of energy. The more frequently that they collide with each other and the more energy they have, the more likely they are to react. So, particles collide with the right amount of energy. Now, do you remember we used a phrase, and that phrase was activation energy, so more than the activation energy. You don't need to be writing this down, by the way, it's just so that we can kind of remind ourselves. Let's have another slide, shall we? Another slide. To increase, I'm going to say R of R, that's rate of reaction, okay? You know what it means, I'm too lazy to write it. You want to increase the frequency with which particles collide. So if they collide more frequently, they're going to react more frequently. And the energy the particles have when colliding. So if you increase their energy, they're more likely to have enough energy, so more than the activation energy, they're more likely to react. So that's what we know already. Now today, as I say, we're looking at concentration. So firstly, let's look at what concentration actually means. As we increase the concentration, there are more particles in the same volume, so a greater chance of a collision. The more concentrated the solution, the faster the reaction. So on the right-hand side, you have a low concentration equals few collisions equals low rate of reaction. Yeah. So you've got acid particles and a marble chip, and as you know, acid and marble react together. So yeah, On the right-hand side, you have a high concentration, which means many collisions, which means high rate of reaction. Okay, so if you can please pause the video, write that down, and perhaps also draw that diagram as well. It's quite a nice one. Okay, so assuming everyone's done that, let's move on. Now, as you know, when you start off doing a reaction, you're starting off your experiment, you get a really quick rate of reaction. So at first you're fizzing and it's bubbling and there's new substances being created and it's all fantastic. But unfortunately, that starts to slow down as the reaction continues. And we're going to be looking at why that happens. So have a look here. Reactions start off quickly and then get slower and slower until they stop. As the reaction progresses, the concentration decreases. I don't know why there's not a capital there. Apologies, let's imagine that's a capital. Frequency of collisions also decreases, and so the reaction slows down. Now you might be thinking, okay, but why? Now I've tried to show that in the diagram here. On the left-hand side, you've got the start of an experiment, the start of a reaction. You've got blue particles and red particles, and they are what you're reacting together. And when you react them together, you make purple. So if you have a look at the next box along, you can see that two of the particles have reacted and made purple particles, and so on and so forth. Now let's go to the third box, the middle box. Now two lots of particles have reacted and made purple. Now can you see that at the beginning of this journey on the left-hand side, you have a high concentration of reactant particles. As you go further towards the right, you have a lower and lower concentration of those reactants, of those blue and reds, which means, as we've just said, a lower concentration means a lower rate of reaction. And so what you find is on a graph, your reaction starts very, very quickly with a quick rate of reaction, but it slows down as the frequency and concentration decrease. So again, if you can please, in a second, pause the video. I'm just going to add a few more labels here. So let's have high concentration of reactants. Oh, that's meant to say reactants, apology. High rate of reaction. And then here, low concentration of reactants, low rate of reaction. So again, please pause the video, make notes on that. You will want to draw those diagrams, so you're going to need 3 colours there, really. It doesn't have to be blue, red and purple, that's not an issue, just 3 colours. Okay, once you've done that, our final bit is about rate and pressure. Now, concentration, fantastic, tends to work best when you've got a liquid. Liquids are easiest things to change the concentration of. But if we are looking at gases, we can do something similar, and we can do that by changing the pressure of a gas. So as we increase the pressure on a gas, we push the particles closer together. They will then collide more often and the reaction will be faster. So can you look at the diagram at the top? On the left-hand side, you have a low pressure. The particles have lots of space to move around, so they don't collide very often, which means a low rate of reaction. On the right-hand side, they've squashed, this is like a syringe or a plunger, and they've squashed it together. So here you've got a much higher pressure. The particles have less space to move around, so they collide more often, so they have a high rate of reaction. And hopefully that's it. Right, so that was all the notes. I'm hoping that you remember what we've been up to, and I shall see you soon. Thanks, everyone.